Well, thank you. Thanks for the introduction. Thanks for everybody for coming. For the first talk, which I hear by French terms is pretty early in the morning. So, sorry. So the premise of the talk is that over the last kind of decade and a half, the way that we're using machine learning really has somewhat changed in a way that machine learning is not something that we're using exclusively for prediction, but that we're using much more for actually taking actions. So if I think about, acting, you think robots and sequential decision making and full reinforcement learning. But I would also argue that all of these systems, ad placement, search engines, recommendation systems, they're all systems where the goal is not necessarily prediction, but the goal is to take the right action at the right time. So I'll take this view of learning policies and learning how to act in these systems throughout this talk. And I think it's going to be particularly important to think about it this way if you think about the data that these types of systems are generating. Right? People use these systems. And when people use them, you get log files. And these log files clearly have a lot of interesting information in them. Information that you can use to kind of measure how well these systems are doing, to optimize their performance, to do learning. And for many of these systems, it's really what they get from their users, the kind of click behavior, star ratings. It's the way how these systems gather world knowledge. Think about a recommendation system. It doesn't watch any of these movies, right? The way that they gather world knowledge is by aggregating all of these noisy bits that they get from basically human behavior. And of course, if you want to do personalization, looking at these log files is probably the only viable source for getting interesting data. Okay, so what do these log files actually look like on an abstract level? So let me try to get some intuition and also a little bit of formalization. So let's start with an ad placement system. So the question is, what ad should I place up here? So you could formalize this as there's a context here. It's the page and the user coming in. And the context I'll typically call X. The system then has to decide to take an action, place a particular ad there. And let's say it's this Malaysia Airlines ad that got placed. And then what the system observes is whether the user clicks on it or not. So this is contextual bandit feedback, right? You get to see the system is in control over the actions, and it gets to see for the particular action that it took, how successful it was. Does it get a click? Does it not get a click? But it doesn't get to see what would have happened if it had taken a different action, if it had placed a different ad. Right? So it's bandit feedback. You don't get full information feedback, but only for the action that you presented. Or think about a news recommendation system. Here, the context X that drives the action is, let's say, a user profile. You know who the user is. The action is, it puts together this kind of portfolio personalized to the user of news articles. And the feedback that you get to see, if you're the New York Times, is you get to see how much time people spend on your site. And let's say that's what you want to maximize, right? Again, you have this type of feedback, context, action that the system took, and feedback that you then observe, but you don't get to see what would have happened if you had put together a different portfolio. Right? And the final example, a search engine. Context is a query. The action that the system takes is a ranking. And then the feedback that you get to observe is how people interact with this ranking, but you don't get to see what would have happened if you had presented a different ranking. So what we want to do is we want to take this type of log data, these triples, context, action taken, the historical action taken by the system that was in operation, and the reward, and learn from this data. So this you can describe as that you want to do batch learning from bandit feedback. And kind of statistically, you can as a probabilistic model, you can formulate this as your contacts, let's say queries or users, come from a distribution P of X, IID. The actions that you selected in the past, that's your system that was running, right? So your past system is part of the data generating process, which already, that makes it a little tricky because you're not kind of independently observing things anymore. You are intervening, and you have intervened in the past data. And then the feedback that you're seeing is from this kind of feedback distribution. And then the goal is we want to learn a new system, pi, so a new policy, pi, that selects better actions, gives you higher deltas, or lower if you think about it in terms of loss. Okay, so that's our problem that I want to address in this talk. And if you think about it in terms of this kind of broad partitioning of machine learning into online learning and batch learning, and full information learning and partial information learning, we're really in this cell here, right? So I would argue that this is the least populated cell of these three, right? There's a ton of work on batch learning and full information, and online learning and full information, and bandit learning in the online case. But what we want to do in exploring this talk is really this cell. How can we get practical, large-scale algorithms to do batch learning from bandit feedback? Okay, so the outline of this talk is, first I'll go a little bit through how could we approach this problem and how have others approached this in the past, and then come up with a kind of learning principle that can guide how we design these types of batch learning from bandit feedback algorithms. And then apply this learning principle to the question of how can we train deep networks from this type of bandit feedback, contextual bandit feedback. And the challenges come up there, and then show some experiments for object recognition and actually on Criteo ad placement data. Okay, so let's formalize the problem a little bit more. So what we want to learn is a policy. It's not necessarily a prediction rule. It's a rule that tells you what action should I take given a particular context. And we'll denote these as pi, and we'll denote this as a probability distribution. So we have stochastic policies that, given an x, have our distribution over y's. You can visualize this in the following way. So let's say this gray box is all the possible actions you can take for this context x. Then policy pi 1 would be a probability distribution over taking these types of actions. And pi 2, another example is a policy that prefers these types of actions. And of course, deterministic policies are going to be just a special case where all the probability mass is on one point, right? Thinking about these as stochastic policies is going to be very convenient later in the talk, you'll see. For these policies, we can then define what's our expected loss or risk, and that's what we want to optimize. So, you would just take the expectation of our feedback delta, of our loss delta, over the actions that the policy takes and the contexts that are coming in IID, right? So, this expectation is the thing that, let's say we stick with losses, deltas are always losses in this talk, that we want to minimize. And you can again visualize this as, the shading here means this is bad outcomes, red, green outcomes are good. Then, for policy pi 1, we would be taking the expectation over this distribution here, so that's mostly red, bad risk, right? Here, this is mostly green, good risk. So we would, this policy is worse than that policy. The problem with that expectation is that we can't actually compute it, right? Where's the problem? Why can't we, right? This thing, that's not a problem. That's our system. We know that thing. We've built it, right? So that distribution we know. This is also not a big problem. P of x, we can get an arbitrary large sample of contexts, users or queries or so. That we can approximate well too. The problem is here, right? Because we have lots and lots of missing information about our deltas, about our losses. As I said before, we only get to observe this delta for actions that we've actually taken in the past, in a particular context. So most of these deltas we don't know, so we can't evaluate this integral directly. So what can we do? Well, we can nevertheless estimate it, and that's A/B testing, basically. So for the policy that was running in the past, it's really easy to get an estimate of that risk. We just take, well, we basically have a sample from this distribution, and we just average the observed deltas. And that gives us a consistent estimate of that risk. If we then want to evaluate a different policy, what we can do is, of course, we can take that policy, let's say pi1, we field it on our system, then we see draws of X, people coming in, right, in a particular bucket. We show them the action that's sampled from that new policy that we want to evaluate, and we get the deltas, we do this averaging, and we get an estimate of the risk. And in principle, we could do that for all policies that we want to evaluate. In practice, that's of course not going to work. We can do that for, a few policies, but we could never do this for kind of an exponential kind of hypothesis space of policies here. It's just too inefficient. So what could we do instead? Well, we could get smarter about how we sample from these policies, that we, how we do the A/B testing, that we don't waste samples or users on policies where we're already certain. We could bring information about how these policies are related, and we could become very smart about doing online learning. And for a while, I've done that, and gives you very beautiful theoretical results and very nice algorithms. And then I tried to get companies interested in implementing these online learning algorithms. And nobody ever wanted to touch them. And I think for good reasons, actually. First reason was, if you put an online algorithm into a production system, there's a whole new way of how this can be spammed and how the company can look bad if that online algorithm goes off the rails somewhere. So what these, what I think typically is kind of a wise, depends on the application, but it's a wise choice that before a policy goes out, it gets vetted through some vetting process. So that you're sure that the policy that you're fielding is reasonable, doesn't make the company look bad, doesn't make the company lose more money than necessary. So that means you really can't change policies on the fly, and that you really can't necessarily give an algorithm interactive control over experiments that you're running online, right? It would be risky. Okay, so I tried to get companies to use my online learning algorithms, and they didn't want to. What they usually came back with was, no, we're not going to do that, but here's a terabyte of data that we have in terms of logs lying around, past behavior on our system, right? Why don't you use that? And for the first few times, I said, well, I don't know. But at some point, I thought, well, what could I do with that, right? So, the problem then becomes, we have lots and lots of data from some old version of the system. Let's call that system pi now, and let's call that our logging policy. And what I want to do is, instead of drawing new data to evaluate each of these policies, I want to use that old data to evaluate all of the policies that I may want to evaluate in my hypothesis space, without drawing new data, without giving interactive experimental control to the algorithm. So that now becomes a kind of counterfactual off-policy evaluation problem, right, in terms of in reinforcement learning terminology. So how can we do this? How can we use old data to evaluate a whole bunch of other policies, even though we're really missing a lot of data about actions that these new policies want to take? The first approach is to build a reward predictor, right? So what I said before was, in this risk, many of these deltas were missing, so we could just impute them, right? We could learn a regression function that says, given an X and an action Y, predict whether the user is going to click or not, right? Predict the rewards. So basically, we have some data here. I want to visualize it this way. We learn a regression. And then for a new point, we could then just fill, let's say this one, we could just fill in kind of the predicted delta and evaluate that interval. The problem is that if you want to do learning, you really have to worry about what's happening outside of the area where you're extrapolating, basically. And you would have to be very careful about maintaining kind of confidence intervals here. Otherwise, you could easily go and be very biased by whatever the bias of your learning method is and how it's extrapolating. So building these click predictors is hard, and many of you worked on this, and you probably agree that it's hard. So I don't want to go this route. I want to go a different route. So can we avoid building a click predictor and still evaluate policies without fielding them on the system? And one way of doing this is through kind of a direct policy evaluation. And if my policy that was running, if the historic policy was stochastic, and it was sufficiently stochastic that it has some probability of sampling the action that my new policy is going to take, even though it potentially never took them, but there was some probability that it would, then we can use these importance sampling tricks, like this importance-weighted estimator, or IPS estimator, where basically we can transform the distribution that collected the data into the distribution of actions that the new policy would take through this simple importance weighting trick. So we take the probability under the old system, that's what we call the propensity of the action, and take this ratio of the two and basically weight the different deltas in this way. And if you do this, you get an unbiased estimate of the performance of the new policy. It's actually very simple. So the idea is that this is the data that you sampled on your old system, pi null, on the logging policy, green being good outcomes, red being bad outcomes of the actions. If you now want to evaluate a new policy, pi here, that has a different kind of shift in probability distribution, then you would upweight these terms, downweight the other ones, the other outcomes. And if you do it according to this ratio, as I said, this gives you an unbiased estimate of what the performance of this policy is. So under these conditions, you can actually now evaluate, using just old data, the performance of new policies. And you can do it for many, many policies. Okay, so let's then, the first thing that you would say, okay, then let's use this IPS estimator as my training error and go through my whole hypothesis space, pi, of policies, pi, and just pick the policy that minimizes this IPS estimate. It's just like, empirical risk minimization. You're minimizing training error, basically. Sounds good, but it typically goes horribly wrong. And here's one of the reasons why it goes wrong. So let's say this is the data, the logging distribution, pi null. This is pi 1 that we're now evaluating according to the IPS estimate. And, it's an average over many kind of moderately weighted terms. So we get a pretty reliable estimate. But you'll probably have some policy in your policy space that maybe puts the probability mass up here. And, you do the weighting, and it gives you an unbiased estimate. But this one point here is going to have a huge weight in this sum. So basically what's happening here, you have an unbiased estimate over one data point. So it has a tremendous variance here, right? So you really do not want to trust the estimator for this policy this particular policy here, right? So if you actually try to derive generalization error bounds for this kind of batch learning from Bandit feedback, you'll see if you want to get reasonable bounds, there's an additional term that you have to take into account because not all policies have the same variance in their risk estimates. For full information supervised learning, this is not an issue because basically for all policies you have, or for all prediction rules, you have as much data as, or the same amount of data. But here you can think about it that for some policies you have more data, for other policies you have less data. And you need to take that into account. So generalization error bound has basically the structure that the true risk is upper bounded by the IPS estimated unbiased estimator of the risk. You have a capacity control term, like you typically do, but you also have this kind of variance term that tells you that, for some policies your risk estimate is worse than for others. As is typical with generalization error bounds, these are pretty loose, but they do tell you how you should be constructing learning algorithms. So you can take away, maybe as a principle, that what you want to do is you want to optimize this type of objective in a learning algorithm. And we call this counterfactual risk minimization because we're going through the counterfactual question of how would that policy have performed if we had used it in the past, right? That's what we're using these estimators for. So you want to optimize training error, the variance of your training error estimate, plus capacity control. So you have this extra term that you typically don't have in supervised learning. Okay, so we have a principle, we have an objective for training based on this type of contextual bandit feedback. Let's put this to work. So how can we take this principle and train a deep network with it? So I'll briefly outline how to do this. I won't actually talk about the training algorithms here because I don't want to go into that much technical details in this talk, but you can check them out in an accompanying paper. And then give results for object recognition and display advertising. Okay, so what do we need to do? Well, we need to define, based on a deep network, a space, what are stochastic policies that are defined on a deep network? And that's really easy because most networks you can already interpret as a stochastic policy, right? If you have a network that, let's say, has a softmax output layer, then we normally think about this as the conditional distribution of class membership, and we use that as part of a likelihood. But you may very well reinterpret this as a distribution over actions, and then it's not a likelihood, but a policy, right? It's a different, so the network or this conditional distribution has a very different meaning, but the form and the shape is the same. So basically most deep learning architectures, and if you have softmax output, that already you can think of as stochastic policy. So don't need to do that much. So then what you would learn is you would learn the parameters of the deep network over inputs and outputs x and y, and you have the conditional distribution of actions given the input. So what else do we need to do? Well, basically we could just take this class of policies and plug it into this objective, this counterfactual risk minimization objective. And it would say, okay, optimize the IPS estimated training error, plus the variance control term, plus, let's say, an L2 regularizer on the weights, or L1, whatever is your preferred method here. That actually worked quite well when we applied it to linear models. And the algorithm that we had there was POEM. It was basically a way of training conditional random fields based on this kind of counterfactual risk minimization objective. But if you go to high capacity models like a deep network, you're running into a different problem. We ran into this a little bit with the linear models already, but for the deep networks, it really became a problem. And that problem is propensity overfitting, we call it. Let me explain what that is or why this happens. So here's a toy example where we have, I think it's 8 different x's, 8 different contexts, and 6 different actions that you can take. And this is the complete loss matrix that we, of course, don't normally know, but it's a toy example. And so the green fields here mean 0 loss. Those are the good ones. The kind of reddish fields mean a loss of 1. What we observe in our training sample based on our logging policy is the kind of the cells that have the blue boxes around it. So that's what we see. The rest we don't actually see. So now let's do this IPS policy optimization here and ask which policies have good value of this IPS estimator. And let's say all possible policies, or it's the exhaustive space of all possible policies here. So we have a very high capacity policy space here. So, well, one policy that's going to look good here is the one that puts all the probability mass on these green fields, right? That is going to have a value of 0 for this expression. Are there other policies that have a value of 0? Actually, yeah, there's a lot, right? You can, like, all the weights, like here. Or this one, right? Essentially, any policy that manages to avoid the training data has a value of 0 here. So if you have a high-capacity model space, then the way to minimize this thing, often kind of an easy way to minimize this thing, is to just avoid all your training data, and that gives you a 0 here, right? So there's basically 2 ways of making this thing small. You either make the delta small, or you make this small, this first term small. How can you tell the 2 apart, right? And the way that you can do it, or one way that you can do it, is by introducing control variate. And the control variate here being that you take just the ratio of this importance weight here without the delta term here. So this is the IPS estimate, right? And this is the same, but without the delta attached to it. And you can see that it's a one-liner, that this always has expectation 1. If you now see that on the training set, it's avoiding all of the data, if it actually managed to avoid all of the data, this will be 0, right? So this can inform, this can tell you whether your algorithm is cheating and avoiding the data versus whether it actually finds good losses delta. And so one way you can put this kind of in as a control variate is as a multiplicative control variate that you just divide by this term. There are many other ways you can put this in as a control variate as well. This is probably the simplest one. So that's the self-normalized IPS estimator, or SNPs estimator. And that has multiple also additional nice properties like equivariance that really make it much preferable over the IPS estimator. It has a slight bias, but asymptotically the bias vanishes. Okay, so let's go back. And instead of the IPS estimator, we're putting in this kind of ratio estimator where we're dividing by this control variate here, but the rest basically stays the same. Again, I'm not saying how to actually now do stochastic gradient on this objective, but you can actually decompose this in a way that you can solve this efficiently. Okay, so let's look at some experiments. The first set of experiments is for object recognition, and we're using one of the standard data sets, the CIFAR-10 data set, which is manually labeled. So there's like an image and what's in the image. And it's a multi-class classification problem. So we're starting with this full information data set and generate synthetic bandit feedback from it. Because this is nice, we can now also compare against what if we had used the full information data set. That gives us kind of a skyline, right? So we can now explore kind of how much we are potentially losing by using bandit feedback instead of full information feedback. And the way to generate bandit feedback from full information feedback is, it's probably what you think it is. You sample an image, or you sample an X, let's say a cat. You then apply a logging policy, and we came up with a logging policy that was pretty crummy. It had a 50% error rate, roughly, 49, I think. And that would take this image, would then make a prediction and say, oh, it's a dog. And this prediction had a propensity of 0.3. You would log that. And then you would just look up the true label and say, no, that was wrong. You have a loss of 1, right? And this is how you then can generate more and more kind of contextual bandit feedback for this problem. The network architecture that we're using in the following experiments is ResNet 20. It was state-of-the-art type of architecture, at least last year. Things are moving fast. But really, the whole thing here is pretty agnostic to what the network architecture is. You can think about this as that you're adding an output layer to, well, at least in principle, any network architecture that you're using kind of for full information learning right now. So here are the results if you do, so this is error rate on the test set here. This is the amount of bandit feedback that we give, contextual bandit feedback that we're giving to the BanditNet version of ResNet. And the green line, this is if you train a ResNet on the full information hand-labeled data. So this is the skyline that you would think is the kind of the best performance that you can get. And so the proof of concept is that if you give, from this pretty crummy policy that has a 49% error rate, if you sample enough bandit feedback, you're converging to the policy that actually has access to the true labels. And I'm not sure whether there's anything to it that is actually a little bit better. That's not significant. So that's good. So it seems that with this objective, you can actually extract the useful information from the bandit feedback. Here's a real-world example, and that's actually on data from Criteo. Here the task is for a given user, for a particular user X, to pick a product Y to put into a single slot banner ad. And the Ys come from a set of about, on average, I think 10 candidate products. There's a candidate set of 10. Yes, and I know that this is not a Criteo ad, sorry. But it seems like every time I'm actually looking for a Criteo ad, I'm not getting one. So something must be going on here. So I'm not sure which competitor this is. But this is roughly what you want to do. You want to decide what product to put in here. At least that's how I understand it. You know that better than me. What we want to optimize, the delta is click-through rate. So we see whether a user clicked or not. The data is about 21 million examples from a stochastic version of the production system that Damien Lefortier collected when he was working with Criteo. And the feature vector also comes from Criteo. It's, after binarizing it, it's about 70,000 binary features. So this data set is publicly available, and it's described in a paper that you can get from my homepage. And we're currently actually organizing a challenge on Crowd AI that uses a version of this data set, where you're welcome to participate as well. It's for a NIPS workshop that we're organizing in a month, I guess. So the network architecture that we're using here is the simplest thing that you can think of. It's a 2-layer 10H activation with 50 hidden nodes. And Artem actually constructed that and ran these experiments. Hyperparameters that we're picking is the variance regularizer and L2 regularizer, learning rate, and Lagrange multiplier that comes from the particular way that we're solving this optimization problem. And the way that those are picked is we're partitioning the data into train, validation, and test. And then we're picking the hyperparameters on the validation set using an IPS estimate on the validation set. And so that's an unbiased estimate. And then you can do, again, hyperparameter selection of that. And then we're using the IPS estimated test set performance on the test set to report. So here are the results. A question?
Yeah, simple questions. So if you're using an IPS estimator and validation set, like what prevents this propensity overfitting using the validation things? Because the regularizer could be turned off. repeat the question again?
Right, so the question was, if we're doing the hyperparameter selection based on the IPS estimator on the validation set, don't we get propensity overfitting again? I guess in principle, yes, right? Just like you get any type of overfitting on the validation set. But since we're only making a few small number of choices, the capacity of this space really isn't that big. So, yes. Oh. Yeah.
I mean, as a follow-up to that question, actually, my main concern is still propensity overfitting. How do we know it's not happening?
On the validation set?
Yes.
Because we're looking at the test set performance.
Yeah.
And
what makes it different? I mean, we've all worked with overfitting at some point, but propensity, I don't think we're mainly accustomed to it. So, is it different from other types of overfitting, or?
It is actually kind of a distinct type of overfitting. One way that you can think about propensity overfitting as opposed to regular overfitting is that in the IPS estimator, let's do it here. In the IPS estimator, you basically have two random variables. One random variable being the losses, right? That's just the same as in normal supervised learning, and you can overfit that random variable. The other random variable that you have is the choices that your logging policy made, right? And you can overfit to that random variable as well. And so that overfitting to that random variable, that's propensity overfitting. And again, you don't have that in normal supervised learning. But again, because you have more information about your logging policy, there's also, I think, interesting alternative ways to address it, like with this control variate, which you couldn't do for the kind of conventional overfitting. So, but I think this is really just scratching the surface in a sense of how you could deal with this type of propensity new overfitting. And it's still going on, right? I mean, just like normal overfitting is always going on in a full information case as well. But you have to kind of balance, you have bias variance trade-offs basically that you're making there. So,
okay, thank you.
But I guess ultimately the test is how well all of this overfitting or not overfitting is happening is once you go to the test set, right? Once you go to the test set, you have an independent sample, and so you again have an unbiased estimate here. So this is just like in normal train validates test setup. This is independent from the training set. So this is not. So these values are not overfit. So this is click-through rate times 10 to the 4. So this is the performance of the logging policy that collected the data, 53. If you just picked randomly from the candidate set, and the candidate set is already a pretty well-selected set, right? These are not random things, the random products in there. So these are probably all pretty good. So you get about a 44 click-through performance. If you take the data from the logging policy and then learn a click predictor as implemented in Vaupel-Warbit, so that's the first approach that I mentioned, you get a performance of about 51 in our experiments. And we introduced pairwise features here to increase the capacity. So you actually don't get better than the pi null. If you use the regular IPS estimator, you get roughly the same performance back. Again, that's the implementation by John Langford and Vaupel-Warbit. So a little bit better. If you put in this kind of doubly robust trick as a variance reduction tool, then that helps quite a bit. And that's, again, a way also to deal with the kind of variance of the estimators. So that helps. And you could apply the same doubly robust trick also to all of the other methods here, and you could probably get another couple of percentage points out of that. Yeah.
So the reference you're using for doubly robust is a big predictor mentioned before.
Yeah, so the regression estimator used in the doubly robust is this click predictor. Yeah. Yeah. And doubly robust is the combination of these two. This is the performance of kind of a policy learning method that we had before, NormPwn. And it's basically optimizing the same objective that I've outlined, but for a linear CRF type of model. So if we now move to BanditNet, the first thing that we've tried just as a sanity check, if you take a linear version, so not this two-layer neural network, but just a single neuron, that should give you the same performance as NormPwn, because it's basically the same model, very similar objectives, and it actually does, even though they're using quite different optimization algorithms, so that's a good sanity check. And if you then actually apply this two-layer neural net, you get a substantial boost over these methods. We tried to look a little bit into where this comes from, and one thing that we've tried is there's a set of features which we call context features. I don't know what you call them. But these are features that are the same for all candidates. They only describe the context. So for a linear model, they don't have any effect. You have to have something nonlinear for them to have an effect. So if we take these context features out, you see a substantial drop in performance. So the network is actually quite good at kind of making these connections between context features and item features. So the nonlinearity really seems to help. Okay, so let me wrap up. So talked about this batch learning from Bandit Feedback, where you have propensity-scored past interventions, and you're learning without interactive control. So I proposed a kind of learning principle, which we call Counterfactual Risk Minimization and the self-normalized estimator, and then applied it to this kind of deep learning setting. And it's led to this BanditNet algorithms. And really you can think about this as a kind of new output layer and new objective that replaces the typical cross-entropy training for your deep network so that you can train your whatever architecture you have based on this contextual Bandit feedback, at least in principle. So I said, the particular optimization algorithms and how you actually do SGD on this and how to do it efficiently, I skipped over this, but you can see this in this paper that's on my homepage. I think it's an interesting area. There's lots of interesting questions. Like this IPS and this SNPs estimator are probably not the final answer to how you should do this counterfactual estimation. These are both kind of important sampling estimators that are known to be unbiased, or almost unbiased, but to have very large variance. They're much better other like matching estimators, balancing weight estimators that one could be using instead. It's not as clear how to do this efficiently, but there's probably a lot of room for improvement still. There's a whole new kind of interesting set of bias variance trade-offs, like this propensity overfitting, which there's probably a better way to address it. And then finally, how to do this not just for deep learning and CRFs, but how would you do something like this kind of counterfactual learning, let's say for a boosted tree, or whatever your favorite models are. If you're interested in, in the papers, go to my homepage. There's also some software. There's a SIG-IR tutorial that we gave on this last year together with Audit. And there's video of that. There's a workshop that we're organizing next month at NIPS that's very much around these topics. And as part of that, there's the Criteo Challenge. So if you're interested in that, you can find a link there as well. All right, thank you.
We might have time for one or two questions, if anyone has.
Just a quick question on the architecture of your BanditNet. It's just a two-layer network?
Yeah, this is really This is not optimized.
Okay,
This is,
exactly.
this is the first and simplest thing that we could think of.
So you could.
I mean, there's probably a lot of room for improvement there as well.
You could stack more layers and stuff.
Yes, I mean, in principle, so as the ResNet, that was a really deep network. And I think the proof of concept is that, you can train a deep, in the previous experiments, that you can train a deep network as well. So I have no reason to doubt that for this other application, you can have a deeper network as well. So.
But if you don't have any more questions, and we can thanks
All right.
Thorsten again.
Thank you.